Hello and welcome back to the deep dive. Today we are wading into some pretty serious waters. We're tackling a subject that at first glance just looks like a bowl of alphabet soup exploded in a data center.
That is a very vivid image.
Hmm.
And, looking at the title, probably an accurate one.
We are talking about the HPE7-S01. To the uninitiated, that sounds like a license plate or some kind of secret government code.
Right.
But looking at the research we've pulled together, this is actually the backbone of, well, pretty much everything exciting happening in tech right now. We are unpacking the certification for building the infrastructure behind artificial intelligence.
It really is. It's such a dry code name for what is, it's essentially a masterclass in modern computing. It's the blueprint for the future.
Exactly. It feels less like a multiple choice test and more like a survival guide for the AI era. We're talking about where big iron, that massive heavy computing power, meets big data.
And that's the perfect way to frame the mission of this deep dive. If you look at the exam blueprint we have in front of us, we aren't just here to memorize answers A, B, C, or D.
No.
We are exploring the actual architecture of high-performance computing, or HPC, and AI. This covers the full stack, from the silicon chips to the software that drives them, and, surprisingly, even the human consulting skills you need to get these massive systems approved and deployed.
That human element really surprised me in the notes, that whole soft skills part, but we'll definitely get to that. Whether you're actually studying for this exam or you just want to understand how companies build the brains behind things like ChatGPT or autonomous driving, you are in the right place. But before we get to the cool, shiny tech, let's just ground ourselves. What are we actually looking at logistically?
Right, just to set the stage, because the stakes are pretty high here. This is a proctored exam. It's not something you can just breeze through on a Sunday morning.
Right.
You have 1 hour and 30 minutes to get through 60 questions.
So that's, what, a minute and a half per question?
Give or take, yeah. And the passing score is 70%. So it's very little room for error. You really need to know your stuff before that clock starts ticking.
Yeah.
You don't have time to second-guess yourself.
Okay, 90 minutes, 60 questions, high pressure. Got it. That's the logistics. Now, let's get into the machinery. I want to start with what I call the engine room, the hardware.
The muscle.
The muscle. One of the first things that jumped out at me in the source material was this really intense focus on NVIDIA NVLink technology. There was a specific question asking about the primary benefit of using NVLink in an HPE solution.
Right. And this is a classic know your hardware question, but it's one that trips people up because they often think, a cable is a cable.
Exactly. The answer provided was that it enables high bandwidth direct communication between multiple GPUs. But I have to play devil's advocate here. We've had cables for decades. We have PCIe. Why does this specific NVLink thing matter so much? Is it just branding?
That's a great question. And no, it's definitely not just branding. To understand NVLink, you have to understand the bottleneck. Think of a standard connection, like PCLC Gen 5, as a standard 4-lane highway.
Yeah.
It's fast, it's reliable, it gets you from point A to point B.
Sounds good enough for most things.
And it is good enough for most things. But when you are doing AI training, you aren't just moving a single car from A to B. You are effectively trying to move an entire city's population to another city and then back again, thousands of times a second.
That is a lot of traffic.
It's massive. In AI training, the GPUs need to share what are called parameters, basically what they've learned constantly. If they have to use that standard highway, the PCIe bus, you get a traffic jam. They get latency. The GPUs stop calculating and start waiting for the traffic to clear.
So the expensive chip is just sitting there twiddling its thumbs because the road is too small.
Exactly. NVLink is like building a dedicated 12-lane superhighway that bypasses the regular road entirely, connecting the GPUs directly to each other. It creates a mesh. The source material highlights that this high bandwidth and low latency are critical specifically for workloads that need that frequent data exchange. Without it, you really can't scale.
So it's not just about speed, it's about the amount of data moving all at once. It sounds like it makes the separate chips act like one giant unit.
That's the key word right there. Coherence. It makes multiple GPUs act like one giant brain. If you cut that link, you effectively lobotomize the system.
Okay, that makes perfect sense. You don't buy a Ferrari and then drive it in a school zone. Speaking of Ferraris, the sources also talk a lot about the NVIDIA H100 GPU. This seems to be the celebrity of the hardware world right now.
The H100 is definitely the rock star. It represents a pretty significant leap forward.
The material specifically asks about a key feature of the H100 compared to previous generations. And the answer isn't just it has more cores. It mentions something called the transformer engine. Now, please tell me this involves robots in disguise.
I wish I could say yes, Optimus Prime would be great in a data center. But no robots here.
Disappointing.
I know. The transformer, in this context, refers to transformer-based models. This is the underlying software architecture behind all this generative AI stuff. Large language models like the one you use to write emails or code.
So the hardware is physically built to be better at running that specific type of software?
Precisely. And here is the real insight, the aha moment that the exam wants you to grasp. The H100's transformer engine can dynamically switch between different levels of precision.
Whoa, slow down a bit. Levels of precision. What does that mean in English?
Okay, think of it like significant digits in math class. Sometimes, to get the absolute perfect answer, you need to calculate to, say, 16 decimal places. That takes a lot of brain power and time.
Right.
But sometimes, in AI, you only need 8 decimal places to get an answer that is good enough for the model to learn. The H100 is smart enough to know when it can use fewer decimal places, moving from a format called FP16 to FP8, to speed up the math without breaking the model.
Well, it's cutting corners, but intelligently. It's optimizing.
Exactly. It's knowing when to sprint and when to pace yourself.
Yeah.
The takeaway for the listener is that if you are designing a system for modern AI, the H100 gives you an efficiency that older generations just can't match because they were doing the hard math all the time, even when they didn't need to.
That is fascinating. It's hardware adapting to the math. Now, moving on from the chips, let's talk about growth. There is a term that keeps popping up in the documentation. Scale out.
Yes, scale out versus scale up. A very, very specific distinction in this field.
The question in the source material asks what scale out refers to in an HPE AI compute cluster. And I love the distractor options here. One of them was literally increasing the height of a single server rack.
Just taller servers, no. That would be funny, but...
The correct definition given is adding more compute nodes to increase total processing power. But why is this the preferred method? Why not just build one bigger computer?
So think of it this way. Scaling up is like taking one employee, let's call him Bob, and just giving him infinite coffee.
Poor Bob. He's going to vibrate through the floor.
Bob works faster and faster. But eventually, Bob hits a physical limit. He can't type any faster no matter how much caffeine you give him. That is scaling up, adding more RAM or CPU to one box. You hit a ceiling.
Okay, Bob burns out.
Scaling out is hiring 10 more Bobs.
And putting them all in a room together.
Exactly. In the context of an HPE cluster, scale out allows for linear growth. If you need double the power, you add double the nodes, you keep the architecture consistent. This is essential for AI because these models are getting so huge that no single computer, no single BOD could ever handle them alone.
So we've got the engine, and we know we need to hire a lot of Bobs. Now we need to figure out what we are actually doing with them. This brings us to part 2 of our deep dive, defining the workloads.
This is where a lot of people get it wrong, and where the exam really tries to trick you.
The sources draw a really hard line between AI training and AI inferencing. To the untrained eye, my eye, initially, it all just looks like AI stuff, computers thinking. But the architecture's totally different, right?
Completely different. And mixing them up is an incredibly expensive mistake.
The source material asks how the design differs. It says, training focuses on massive parallel compute, but inferencing focuses on something else.
Low latency and predictable response times.
Okay, let's break that down. Why are they so different?
Okay, imagine training is like a university education for the AI. It's reading the entire Library of Congress, processing these massive data sets, trying to understand patterns. It takes days, weeks, maybe even months. It's heavy lifting and needs massive throughput.
That's the massive parallel compute. It's just crunching numbers in a dark room.
Right. Now, inferencing is when the AI has graduated. It's out in the world doing a job. You ask it a question and it gives you an answer.
Like when I ask my phone for the weather or asked ChatGPT to write a poem about my dog.
Exactly. And that needs to happen instantly. If you are in a self-driving car and it sees a stop sign, that is inferencing. It needs to decide, stop right now. You can't wait 5 seconds for the server to think about it and check its notes.
So training is about raw power over time, and inferencing is all about speed of response.
Yes. Training is a marathon. Inferencing is a sprint.
So you don't just go and buy an AI server. You have to ask, are we teaching the AI or is the AI already working?
Exactly. If you buy a training rig for inferencing, you're just wasting money because it's overkill. If you buy an inferencing rig for training, you'll never finish teaching the model because it's just not strong enough.
And part of that architecture, and this is a big one, is storage. We have these super fast H100 GPUs. They are expensive. How do we keep them fed with data?
It's the bottleneck problem all over again. It always comes back to bottlenecks.
The source question asks for the most critical storage characteristic for a large-scale training cluster. The answer is high sequential read throughput and low latency access. Why sequential? Why not random access?
Think about how AI learns. It ingests data. It reads a data set from start to finish, then it does it again and again. It's a stream of information.
Like drinking from a fire hose.
Exactly. You have spent millions of dollars on these H100 GPUs. They are hungry beasts.
Yeah.
If your storage is slow, if that fire hose is just a garden hose trickle, those GPUs are sitting there idle.
That's the GPU idle time mentioned in the text.
Right. And GPU idle time it's basically burning money. If your GPU is waiting for data, you are paying for the power, the cooling, and the depreciation, but getting zero work done. So the storage needs to be a fire hose. That's why sequential read throughput reading data in order very, very quickly is the #1 requirement.
It's interesting how everything keeps coming back to this idea of don't let the expensive things stop working.
That is the golden rule of HPC. Keep the beast fed.
Okay, so we've built the hardware, we've scaled out, we've selected the storage, but a computer without software is just a really expensive space heater.
A very loud, very expensive space heater.
Yes. Let's look at the software layer. The sources mention something called HPE Private Cloud AI developed with NVIDIA. Now, I see cloud and AI, and I immediately think, okay, marketing buzzwords. What is this exactly? Is it just an operating system?
It's much more than that. The term they use is an integrated AI software stack.
Integrated stack is also a bit of a buzzword. What does it actually do for me as an engineer?
Okay, so imagine trying to build a modern car where you have to manually code how the steering wheel talks to the tires, and then write a separate driver for the brakes, and hope they're compatible with the engine software you downloaded from some forum.
That sounds like a complete nightmare.
That is what building AI infrastructure from scratch feels like. You have drivers, libraries, frameworks like PyTorch or TensorFlow, orchestration tools like Kubernetes, and they all have different versions.
And if one version is wrong,
The whole thing breaks. We call it dependency hell. You fix one thing, and 2 other things just fall apart.
so this private cloud AI solution basically pre-packages all of that for you.
Exactly. It gives you the drivers and the frameworks pre-validated. It simplifies the deployment so that data scientists can focus on building models, not on debugging why the server can't find the graphics card.
That seems worth the price of admission just to save your sanity. But there's a trap here. The sources bring up a really tricky scenario involving virtualization.
Ah, yes. The virtualization trap. This is a favorite topic for exam creators because it tests if you understand all the layers.
The question asks what an architect must consider when running AI workloads in a virtualized environment, and the answer is the performance overhead on GPU pass-through or partitioning.
This is critical. Virtualization, running virtual machines, it's great for flexibility. It's how the cloud works. But it adds a layer of software management called the hypervisor between your software and the hardware.
And for AI, that layer is kind of like a middleman.
A middleman who likes to check the paperwork on every single packet of data that goes through.
That sounds slow.
It can be. The source warns that if this isn't configured correctly, you get performance overhead. Basically, the hypervisor slows things down. If you don't configure GPU pass-through, which effectively tells that middleman to step aside and let the software talk directly to the GPU, you reduce throughput.
So you could have the fastest chips in the world, the H100s. But if your virtualization settings are wrong, you're basically driving with the handbrake on.
Exactly. And the exam expects you to know that risk. You have to balance the flexibility of virtualization against the raw performance need of the AI. Sometimes you just have to strip away the virtualization to get the speed you paid for.
This transitions us perfectly to the final, and honestly, the most surprising part of this deep dive. We've talked silicon, we've talked software, now we have to talk about people.
The human element.
Part 4. The architect as consultant. I was surprised by how much of the source material focused on soft skills. I thought this was a technical exam. Why are we talking about, feelings?
It is a technical exam, but it's a solutions architect exam. And the solution isn't just hardware, it's solving a problem for people, for business.
There was a question about presenting a validated solution design to a customer. It asks, what is the most important element to include? And it wasn't technical specs or blueprints.
No. The answer was clear evidence of how technical specifications meet business goals.
Why is that the most important thing? Isn't the customer paying for the specs?
Customers don't buy H100s because they like the way they look. They buy them to solve a business problem. Maybe they need to speed up drug discovery or detect fraud faster or recommend better products to their customers.
Right.
As an architect, your job is translation. You have to be able to look the CFO in the eye and say, we selected this expensive NVLink storage, not because it's cool, but because it will reduce your time to market by 20%.
You have to connect the wire to the wallet.
Exactly. If you can't justify the business value, the project doesn't get funded. You can have the best design in the world, but if you can't sell it to the board, it just stays on paper.
That connects to another acronym I saw in the text, CID.
The customer intent documentation.
It sounds incredibly bureaucratic.
It sounds boring, I know, but it is an absolute lifesaver.
The source asks what the primary objective of the CID is. And the answer is to ensure the final solution configuration matches the customer's technical requirements.
Think of the CID as the contract of understanding. It captures what the customer actually wants and needs, not just what you think they want.
So you don't end up building a Ferrari when they asked for a minivan.
Exactly. Or build a minivan when they needed a rocket ship. It reduces the risk of misinterpretation. You write it down, you validate it, and you confirm it. That way, when the system arrives, nobody is surprised, oh, I thought this would fit in our standard rack. No, the CID says you have high-density racks.
It protects you.
It protects everyone. It aligns expectations.
But what if, and this is the classic consulting nightmare, what if the customer doesn't really know what they want?
That happens, I'd say, 90% of the time. We want AI. Okay, what kind of AI? The good kind.
The source poses this exact scenario. As a trusted advisor, what should you do when customer requirements are unclear?
And what were the wrong answers? I love the wrong answers on this one.
One was, recommend the most expensive solution to be safe. Another was just, select a random configuration.
Please never do that. That is how you get fired.
The correct move is, ask clarifying questions.
It seems so simple, but it's profound. The architect's job isn't just to answer questions, it's to ask them. It's structured inquiry. How much data do you have? How fast do you need answers? Is this for internal use or is it public-facing?
So you're a detective.
You are. You are investigating the business to build the right technical solution. If you guess, you fail. And in this field, guessing can cost millions of dollars.
It really paints a different picture of this role. It's not just a tech wizard in a basement. It's someone who can walk into a boardroom, understand the strategy, and then go into the data center and actually wire up the ND-Link.
That's that full stack mind we talked about at the beginning. You need to speak Python and you need to speak finance.
Thank you so much for guiding us through this machinery today.
It was my pleasure.
And thank you to everyone listening, whether you're prepping for the HPE7-S01 or just trying to keep up with the AI revolution. We hope this deep dive gave you some solid nuggets of knowledge to take away. We'll catch you on the next one.